Okay, guys, so let's start uh, understanding how the moment curvature graph is done, no? Using with the help of a MathCAD application software. So for the given assumptions and parameters here, we take note that this plot of the moment versus curvature is for under reinforced beams. Okay, wherein your AS provided, or this AS that is provided, is always less than the balance condition. So without taking into consideration the provision of the code wherein a maximum still area is the basis for assurance of ductility. So here, since this is generic, we we assume that the balance condition is our reference point in dealing with uh, the ductility behavior of the beam. And if AS is less than ASB, then you call your beam an under-reinforced beam. So these are the given parameters. I'd like to apologize, the units are not given, but my assumption is that the unit used here are in megapascal, millimeter, and millimeter square, okay, for area, and also Newton for force. Okay, so all stress units will be in megapascal, all dimensional units may be for length and area will be in millimeter, and all forces will be in newtons. So for a consistent manipulation of your calculation later, this is, or these are the units that were used here. Okay, so we have here a beam, singular reinforced area, AS 600 is must, okay, be less than AS balance. So I did not check it, but maybe you want to check the compliance of such condition here. If it is met, please simply solve for your AS balance. Okay, so in our previous lecture, I discussed to you what curvature is. Okay, on the uncropped elastic stage, what happens is your beam bends elastically, and the determination of such strain compatibility, which exists in the elastic stage, will be defined by the neutral axis on the basis of your KD, and is computed by what? Using a transform section method. So you are simply taking into consideration the geometry of the section. So the basis for your location of the neutral axis is most on the geometry of the section. And since the material property of steel is not the same as that with concrete, then we are forced to transform the steel into a concrete section, as we have done in our previous discussion. And in this case, we derive a formula on how to deal with it for a singular reinforced beam rectangular section. This formula is now valid. So I just I computed the value of your KD. So I just inserted a number 1 there to indicate that you are on the stage 1 uncropped elastic stage. So you can do a computational procedure on locating the neutral axis differently, but I'm sure the value will not differ much with this value. Okay, so in the uncrack stage, we need to solve for the cracking moment. Why? Because we have to plot the moment curvature from an initial loading, which have to start from 0 up to an initial loading uh, producing a cracking moment given or as defined in the ACI. Because the uncrack property will no longer be the same as that with the crack property, then we have to set a limit of the uncrack elastic behavior, and that limit happens to be the limit in which the beam will crack. So we have to compute for the cracking moment, and these are the formula we need to get the cracking moment. So it's a simply a flexural stress formula, which is F is equal to mc over I. Okay, so of course this must be uh, uh, the value used here must be appropriate to the behavior in the uncracked elastic stage. M is the MCR, C is H minus KD1, so this is your C, this is your M, and this is your I. Okay, again your I is only assumed to be the gross moment of inertia if you want to solve the IU here better, because IU represents the moment of inertia at the uncracked stage. But ACI allows us to use this, since later you will notice that the measure, no, the level of magnitude of IG will not differ with IU, but of course still IU must be greater than IG. Okay, so upon solving the cracking moment now, we proceed with the solution for solving the concrete stresses in compression. And the concrete stresses in compression, since we are still in the elastic stage, will simply be again mc over I. And we start here from FC1. Okay, so this is actually the limit for your crack elastic stage, which has an equivalent strain. Okay, so this provides us a scenario where Hooke's law is uh, applied. Okay, so using Hooke's law, which is applicable within the elastic behavior or elastic stage, then epsilon C1 is simply this value. Okay, so we are now setting your moment limit M1 must be equal to MCR here. Okay, and your curvature now will simply be equivalent. The limit for curvature P1 will simply be epsilon C1 all over KD1 as defined in your figure here. Okay, so let's use this figure. Although this is the cracked elastic stage, this is the uncracked elastic stage. So let's use this. So this is simply EC over KD. And at point 1, it's the limit upon which the beam will crack. This will become EC1 all over KD1, which gives us a value of P1. Okay, so I just use now a MathCAD tool to automatically provide us with these two values, M1 and P1, to enable us to plot. Okay, later in our graph, I will show you where these values are plotted. So for stage 2 crack elastic stage, the same case is done, no? The only difference is that we have a KD2 now available for us. And the section is now a crack section, but still we are on the elastic stage. And the determination of the location of the neutral axis, KD2, can be simply evaluated using the formula again we have derived in the previous lecture, which is this one. Okay, so your moment of inertia now will no longer be IG or IU, but rather it will be ICR. And we have again another limit for M2, which is MCR on the crack elastic stage. So this is now two boundaries, two sets of cracking moment in one instant, because at the snap of a finger, let's say the beam now transforms from an uncracked beam to a cracked beam. So there's a sudden jerk. So there's a sudden jerk in the resistance of the beam for the moment, and that is the reason why the older codes and even the new codes uses the raw minimum. So this is due to the cracking stage. Okay? So mabibigla yung steel kapag nagkaroon ng sudden crack, at kung yung raw mo is not enough to handle the cracking moment, because raw may be derived only from the capacity determination, then there will be a brittle failure. So that is the reason why the code gives us a raw minimum value for it. Okay? So just continue doing the computation. FC2 is MCR-KD2 over ICR, and epsilon C2 is FC2 over EC. Then we need these two values, of course, EC2 and KD2 to plot or to determine your curvature P2. Okay, so again, by using MathCAD, we just simply make use of the equality sign or equal sign to produce us the value of M2 and Phi2. Okay. So for stage 3, we have the crack inelastic stage, which starts from KD2. So this is the last point upon which your beam has already behaved. And the technique for looking into...
Sir, excuse me, nakamute po kayo.
Okay. So we are now on the crack inelastic stage here, and we have to start at the point wherein C is equal to KD2, because this point here is the last point upon which our beam behavior was computed. Okay, this is the last point upon which the curvature was computed in terms of this value. So the technique for doing the crack inelastic stage is by the use of what you call the iterative approach. Okay, so we just assume a value of C, and C is simply equal to what? Your KD values. Okay, so C here is simply KDs in the elastic stage. So pag C yung nakita nyo, ito inelastic ito, no? Kapag KD yung nakita nyo, ito is elastic. Okay, so I have here a MathCAD tool for solving the value of your steel stresses using a simple what they call this in MathCAD. So this is a simple tool, programming tool, to iterate or so to solve for your fs at all values of c ranging from 1 to kd2. Okay, so this is now your formula. If you don't have a MathCAD, you have to solve it manually, one by one, by simply substituting the value of c here in this equation. So it is doable in manual, but it is highly tedious and boring not to do it. Okay, for your phi 3, okay, now we can assume a function. So this is a functional expression. So phi 3 is a function of c. And we know that curvature is simply equal to strain all over your distance from the neutral axis. Okay, so this is a simple function. That's why automatically MathCAD will just put one by one the value of c iterated from 1 to kd2, and also epsilon cu, while epsilon cu is a fixed value coming from the ACI code. So this is now the ACI definition of your crushing strength of concrete. Okay, so M3C now is simply equal to a simple formula ASFS sorry, ASFS. We are not using JD in strength design, so we are using D minus A over 2. Okay, so computing it on the point at which C is equal to KD2, I just tested it, and it will yield the value of 4.964 times 10 to the 7 Newton millimeter. Since this is a Newton millimeter unit, we can convert it later to a kilonewton meter by simply dividing it by 10 to the 6. Okay, so let's have a summary of what we have done so far. No? So the moment and the curvature here are now summarized in terms of a vector. Okay, so we start from 0 moment. We first then we tabulate the first moment at the uncracked elastic, then the cracked elastic, and the cracked inelastic. Okay, so you'll notice that in the cracked inelastic, there's no fixed value because M3 is a function now of your KD2 here. Okay, so whatever KD2 has, it will give you later. No? KDs are different values, so it will give you what a series, no, of m's, which will be added to this vector to complete the moment curvature graph. Okay, so these are all fixed points, and these fixed points corresponds to a value of phi which are also fixed. Okay, and these are the values, the actual values. No, so these are the the values of the vector in terms of the variable, and these are the values in terms of a real number. Okay, so this is now plotted here, and you will see now the sudden jerk that I am talking about a while ago. So this is actually at the point of cracking. Okay, so this is the elastic uncracked section, then it will crack. So you have here an elastic uncracked section. Sorry, elastic crack section here. So this is elastic, or let's use the term used in the presentation. So this is the elastic uncracked. So this is the elastic crack. and this is the inelastic graph. Okay, so this is quite tedious to deal with when you talk of moment curvature. So in my actual application class, I am not interested with some points here. So I'm just trying to tell you now the practical side of everything. No, since we are mostly, especially in elastic, or sorry, in the plastic analysis or plastic design procedure, which happens to be the ultimate, the culmination of all what we are doing in design. You only expect to look into what is happening somewhere here. Okay, so if I will not uh, consider the stages here, it is simpler to graph the moment curvature by using the strength properties of your section. What do I mean by the strength properties? So the strength properties uses a strength design method, no? Okay, so I use the strength design approach to deal with the moment curvature relationship. So this is what you will see on some presentations when you talk of actual design. So what happens there is I simply will have a plot similar to this. Okay, so it will just ignore the elastic and crack, and then somewhere here it will smoothly curve like this. Okay, so again, what I'm trying to tell you is practically what you are interested on in the moment curvature relationship is here. Because when you talk of pushover analysis, this part here is still on the immediate occupancy performance rating, no? So, pag lumindol, pagdating dito, wala namang problema yung building. Pwede na kayong bumalik sa building. Pag yung design mo nandito. Okay. Pero pag yung design mo nandito sa point, I think this is a point B and a point C, somewhere here. Okay, a point B and a point C, wherein the life safety and collapse prevention is now the thing of significance and importance, then ito yung mga values na kailangan na tamang-tama, no? Hindi ko sinasabing hindi importante ito, pero look at the procedure and how to do it. It will take you time. That's why in software, I have not checked it, but I'm sure they ignore what is happening on the elastic stage, especially when you're talking of pushover approach in your design. If you have heard those limit analysis performance based approach that they are talking about, that's all about it. No, you just set a moment curvature property of your member in terms of axial, flexural, shear, whatever you want. Okay, and then try to make use of an incremental loading to see whether the strength, moment strength, axial strength, shear strength of the curve actually passes this region of performance, which are the region of life safety and collapse prevention. So if I were to look into some of the designs, especially yung mga buildings na government, they are on this level, no? I happen to analyze a school building, and the level of safety in terms of performance is on immediate occupancy. Nandito sila before B point, no? And that's good because school buildings are very essential buildings. But when you're talking of performance in terms of some special structures, which cost a lot of money to build or create, you have to consider, I think, life safety only. Yung collapse prevention, panghuli na yon, no? Pag nagkamali ka ng konti at chinek mo, at least hindi magko-collapse. And that's how uh, design, structural design approach in terms of safety is now being what is now being looked into, but in terms of performance based na tayo ngayon kasi, no? That's why you need to know how to do this. Okay, so that's the more practical side of what I'm trying to show you right now. So if you have some concerns and questions later, so I'll address it, okay, after this video. Thank you very much.